I'm going to show you something, and I'm going to ask you a question. What do you see? Okay. 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 All right. Well, I'll tell you what I see. I see information. Okay? I see gaze. Where's this person looking? What are they interested in? What are their priorities? What are their preferences? I see the pupil. I see blinks. I see tears, all of which tell me about the internal state of this person. I see the retina, which tells me about the health of this person. I see the iris, which tells me about the identity of this person. And I see the cornea, which reflects the world around this person. So what I see over here is a lot of information about this person, all contained in the eyes of this person, right? So my research at the University of Florida is really driven by a very poetic question. And the poetic question is as follows. Are our eyes the windows to our soul? Yeah. Poets and philosophers have asked this question for a very long time. And the interesting thing is that it has a lot of practical value. I'll show you here. These are 4 selected grand challenges from the National Academy of Engineering, all of which are enabled by eye tracking and drawing inferences from people's eyes. Enhancing VR, securing cyberspace, personalizing learning, and autonomous vehicles. I have interest in all of these and more. Today, I'm going to talk to you about 3 projects. First, I'm going to talk to you about quantifying attention for UX design. This is a YouTube-funded project, and I'll give a kind of a short presentation on what we found, what was our experiments and what we found. Second, I'm going to give an overview of the work that we are doing on performance analysis and on perception for virtual avatars. So because of the length of this presentation, I'm going to do kind of a little bit of a high-level presentation at the overview level, but I'm always happy to answer questions either between the talk or after on details. So quantifying attention for UX design. Now, to this crowd, I don't have to talk about online e-commerce and how many millions and billions it is worth. UX design for e-commerce has mostly converged to a shelf-style layout. Right? You have a thumbnail image and you have a text. Right? The big open question, given this kind of UX design, is what is the relative importance of the picture versus the text? Right? This is important because this really tells you how to lay out the picture, how to lay out the text, what should the look and feel be. Now, there's a lot of work in cognitive psychology, media, education, and so on, looking at this question, the relative importance of picture versus text. We know that there is a clear picture superiority effect. What that means is there's evidence to show that pictorial information is better remembered, picture captures more attention regardless of size. All of this is backed up by what is called the dual coding theory. We also know from this literature that people have looked at how pictures and text are integrated. We know that there are integrative saccades, which means that a user switches from picture to text and back. And we know there's something called the spatial contiguity principle, which means that when pictures and text are placed near to each other, there are more integrative saccades. And finally, what this literature tells us is that there is a task effect. So researchers in cognitive psychology have found that if you were to ask people to look at advertisements for the purpose of judging aesthetics, they spend more time looking at the picture. Whereas if you ask them to buy a product, they spend more time looking at the text. So there's a lot of evidence. It's kind of given the scenario that we're going to consider, it kind of doesn't converge to one nice answer that we would like to have. The scenario being, it's Friday night and the user has some free time. The user is browsing through YouTube and looking for something to watch. So this task is closer to buy a product. And what that means is we might expect that there is more attention to the title text relative to the thumbnails. However, because of the layout, there's high spatial contiguity of picture and text. And what that means is maybe there will be a lot of integrative saccades, so the user will switch back and forth. And that might suggest that equal amounts of time is spent on both of these pictorial UX, both of these UX elements. Right? So which one is it going to be? Our key idea here in this project was to eye track participants. So we call people over to our lab, give them a task, and we eye track participants as they browse this website. 23 participants under an IRB approved protocol were eye tracked, and their data looked something like this. So what you'll see is a circle over here that marks their gaze. It's a little bit faint over here. And you'll see that we have annotated events such as title text attended first, thumbnail attended first, and so on. We collected gaze position, we collected screen capture, and we collected session start and end times. Okay. We did control a few things. A trial was considered the time between the homepage loads to the time the user clicks on their selected video. So we wanted to know, what do the users do in order to click on some video they want to watch? We asked the user to click on the YouTube icon and go back to the homepage after watching the selected video. And what this did was to align the gaze at the start of each trial. We removed the keyboard to prevent users from using the search bar because we wanted them to browse. And we did not allow them to sign in. So even though the web page was live and that introduced some variability into what each user saw, at least they did not sign in. So everybody saw the generic homepage. So our preliminary analysis showed that the watch durations were all largely greater than 30 seconds. And that indicates when users selected videos, they liked the videos that they saw. So it was a good high watch quality. We also found that if we were to look at their entire session, which is the duration of time that they spent in the lab, they spent about 20% of their session browsing the home page. Right? So all of this told us the data that we are getting is good data. We can start working and doing further analysis on this data. After this, we manually coded the screen capture that we had done. We marked out areas of interest that corresponded to the thumbnails and areas of interest that corresponded to the title text region. Now, these areas of interest are fairly small, but we had calibrated it so that we are still able to get reasonably good confidence that people are looking at one area of interest versus the other. Okay. After this, we had annotators look at the video that I just showed you and mark events. These events included, were the thumbnails viewed first, were the title text viewed first, were both viewed, and so on. Right? So fixations 2 are examples of thumbnail being viewed first, and fixation 6 is an example of title text being viewed first. What we learned from this is that only thumbnails are viewed more than thumbnails and title text together. We also found that if only one AOI was visited, then thumbnails got almost 3 times, or more than 3 times, I should say, visits than title texts. So what this is telling us is thumbnails are, this is pointing to the fact that thumbnails are important, much more so than title texts. We did an AOI analysis, and when we looked at how many unique thumbnails were viewed versus how many unique title texts were viewed. Almost twice as many unique thumbnails were viewed. We looked at which AOI was looked at first. Was the thumbnail looked at first or the title text looked at first? Thumbnails were more often viewed before title texts. And this relative preference to view thumbnails first was consistent across participants. So if we broke it down by individual participant ID, very consistently participants viewed thumbnails first. So all of this evidence taken together is telling us thumbnails are viewed before and thumbnails are viewed more than title texts. Right? So what, maybe if UX designers had to guess at it, they might have guessed this. The question is that just because thumbnails are bigger? Is that what's going on? Thumbnails are typically 1.68 times the area of the title text, and thumbnails are generally bigger across. It's not just YouTube's website, across if you take different UX, different websites. If we were to account for this larger area, they're still looked at 10% more than title texts. So the takeaway now for UX designers is thumbnails catch eyeballs. And the takeaway for content creators is, of course, choose your thumbnails well. So this experiment told us this and opened up several questions after that. For example, if we want title text to get more attention, should we make the title text bold? Maybe we want to make it bigger. What should we do? What are the characteristics of thumbnails that cause it to be looked at first? Right? Is it thumbnails that have faces on them? Is it thumbnails that have a greater contrast from the background? What is the characteristic of a thumbnail that catches attention? If we wanted to do this automatically, how might we suggest thumbnails? How might an algorithm suggest thumbnails to content creators, and so on? So this was our work on quantifying attention for UX design. What I'll do now is talk to you briefly about some other projects where we have used eye tracking and perception in different ways towards different applications. So eye tracking is now being built into virtual reality devices. This offers a very nice environment for eye tracking because it's controlled. You can calibrate it exactly. The user is not going to move. It's going to be attached to the head. VR eye trackers, VR headsets are having eye trackers built into them. And the applications mostly that they are enabling are to do with the use of gaze. So gaze locations for foveated rendering, gaze locations to help do multimodal user interfaces. So if you're looking at something and you want to select it, that makes it easier. Right? It's also being used for a variety of enablers for social VR. If you have a social avatar, it has to have good eye contact and good eye movements. Eye tracker is a critical enabling technology for that. We were interested in if we could use more than gaze, if we could use the pupil in addition to the gaze to be able to do things like performance analysis. Can we understand the internal state of the user from this information? So let's look at the literature. Folks in psychophysiology, psychology, have long studied the pupil as an index of many, I should say, components of the internal state of the user. If we look towards the literature, we'll find that the pupil is an index of emotional arousal, pupil is an index of cognitive load, pupil as an index of kind of different kinds of affect and stress. Right? In our own work, when we did experiments, we found that the pupil could be used to infer when a zombie attack was occurring. So for all those who are a little bit queasy about horror films, now's the time to close your eyes and ears. I'm going to play out a short little clip, just 2 or 3 seconds. And what you'll see over here, these are these tracks. So these are a bunch of people looking at this video. And what you see at the bottom is an index or a score that's derived from the changes in their pupil size. I won't go into the details of that. Just look at the blue curve, right? You'll see the blue curve rise when the zombie comes in. So the zombie comes in, everybody's pupils increase in size. The challenge in using the pupil as an index for the internal state of the user is that in real-life applications, brightness causes the pupil to change as well. So the pupil regulates the amount of light entering the eye, and that's one of its primary functions. So I'll show you one of our experiments over here. This person is looking at a black slide like this. The pupils are quite large to start with. Look at the black circle. It shrinks in size when a bright slide is flashed. Right? This is known as the pupillary light reflex. So we said, okay, well, if we could characterize the light reflex, if we could model it, it would become a known quantity. And then we could account for it in any kind of index that we are deriving from the pupil. So what we'd like to be able to do is have a function that has brightness as input and provides the pupillar size as output. Now, an intuitive functional form is the line, right? When brightness is large, pupil size is small. When brightness is small, pupil size large. Right? Now, you might point out, well, the pupil is not going to respond in the same way at all brightness levels. Maybe your curve, your functional form should look something like this. Or you might say, you should really flatten it out, right? Maybe your functional form should look like this. And then somebody may point out that you need to have a little bit of lag in the pupil because it's not going to respond immediately. And then somebody else may point out that you need to account for adaptation. So the history matters. If you've been seeing bright for a long time, that's going to change how your pupil behaves to a certain input. And all of you are right. So if we, once again, look towards ophthalmology, optometry, vision science, folks who have studied the functional form of the pupillary light reflex, will find that they have proposed a few different models for the pupillary light reflex, right? With some differences that we need to account for when we are looking at it from the kind of computational applications point of view. The first is that we want a model that models the pupil size as a function of grayscale intensity. That is our focus. The reason for this is that then we can predict what the pupil size is going to be based on the pixels that we are going to render. So we don't have to add additional hardware onto the VR headset, which measures the amount of actual light in terms of lux and lumens, right? We can do that if we want. Right now, for our purposes, we don't want to add additional hardware. The second is, we want a functional form that we can fit to the particular user. So if you were to think of it as a line, somebody is going to be this line, and somebody is going to be this other line. So we'd like to be able to devise calibration procedures that will help us fit the functional form to the individual user. We want this calibration procedure to be very, very simple, something that we can do within the login of a VR headset, right? The person puts it on, they're logging in, we've calibrated them. And then we want some kind of a test procedure to figure out how good is this functional form. So this is our focus. For the purpose of this talk, I'll just use the linear model, right? Knowing that it has limitations and caveats, I'll just use the linear model and talk through it. Okay, so our calibration procedure that we proposed is as follows. We flash grayscale slides of varying intensity to the user. We do 1 second on, 8 seconds off. So here's what the data looks like. On the vertical axis, I have pupil diameter, and the horizontal axis, I have time. Okay? So what you're seeing over here is how one particular user's pupil is changing over time as we are flashing slides at them. So they look at a slide of grayscale intensity 32 for 1 second, and then it's off. You'll see that the pupil comes back to its big size, right, or to its best size. Then slide of intensity 64, 96, 128, 160, 192, 224, 255. And each time you'll see that the pupil constricts, and the constriction becomes more and more as the slide is brighter. So this constriction point, this radius, is what we take as the pupil size for this intensity. So 32 and 4.3 centimeters, sorry, millimeters. So 32 and 4.3 millimeters, that forms a training pair. Given these training pairs, we can fit a line to it. Yeah, that's just regression, so I won't talk through the details of that. Now comes the question of how are we going to test this? Well, the naive way to do it would be, we have 8 training pairs, just leave 4 of them out, use 4 to fit the model, and use the other 4 to test. Okay, fine. The problem with that is that all of our deployment scenarios involve continuously changing brightness. And our test mechanism does not account for that. So we devised a test procedure, and it looks like this. We called participants into our lab, and we showed them a video, right? And we are tracking their gaze as they are doing it. The X that you see over here is the gaze of one person in these 2 frames of the video. The square marks a 1-degree foveal neighborhood. The average intensity of the square in each case is different. We take the average intensity of this square and we create a grayscale slide with it. Okay. Now, for each frame of the video, we have a grayscale slide. And this grayscale slide is changing in brightness with the same kind of temporal variation as would be encountered in a video. Okay. I want to point out that this is not randomly varying grayscale brightness, because randomly varying grayscale brightness does not have the same statistics as the changing brightness when you watch a video. So this is an ecologically valid test paradigm. If we show a person this video, what we have done is we have a mechanism to be able to measure their pupil diameter without it being containing any aspect of emotional arousal, cognitive load, affect, anything like that. It's just a response to changing brightness, but this changing brightness has some statistics to it. Okay, so we use this. What you see over here is the measured pupil diameter in black and the prediction of all of these different models that we tried. And all of the models tested similarly. You couldn't say which one is better, which one is worse in any kind of reasonable way. The reason for that is actually quite simple. These models that we tested did not account for adaptation. They were instantaneous models. Right? If we look at these models for 2D eye tracking, which means people are watching things on a screen, versus VR, right? This is what you see. So here we have 5 people, same individuals on 2D and in VR. Right? So the physiology is the same. And we fitted a light reflex model to each of these 2 individuals. So to each of these individuals in the 2 settings. The dotted lines correspond to the 2D case, and the solid lines correspond to VR. And what you'll see is that all of the VR lines are lower than all of the 2D lines. Yeah. So this tells us that the model must be calibrated for each device, right? And of course, brightness is more in VR HMDs compared to when people are watching things on a screen, because your projector and bulb is just so much closer to the person's eyes. Right? Okay. So what we have here now is a framework, a mechanism to be able to calibrate and test for various models of pupillary light reflex. And given this framework, we can test linear models, nonlinear models, say univariate models, multivariate models, and so on. The big open question for VR is how to account for depth. So everything that we have done is the model of pupil changing as a result of light. But in VR, depth also changes, and that also changes the pupillary size. So what we really need is to account for that in order for this to become usable for VR. So these are all things that we're interested in and starting to work on. Now VR is not just about watching videos or virtual experiences, go under the sea and so on. A very big driving application of VR is social VR. We can imagine connecting to our friends and our family and our colleagues in a virtual world, right? And we're all going to have avatars in this virtual world, right? I'll talk to you now about a little bit of work that we are doing in terms of generating virtual avatars. And we'll soon be doing this overview. Okay. All right. So in terms of virtual avatars, I want to take a moment and think a little bit about where we are in the field of graphics and vision, right? If we were to take the combined knowledge in the fields of graphics and vision, we have a pretty good understanding of how to generate avatars for adults. We know how to model the geometry. We know how to generate appearance. We know how to generate motion, right? We haven't crossed the uncanny valley yet, for sure. But we are confident we have the fundamentals worked out, and we are working along the rest of the way. Things are going well. Here's an adult. Right? We call this adult to our lab, and we told this adult to run as fast as you can. And here's what he did. And then we called a child to our lab, and we asked him to run as fast as he could. And that's what he did. So in this virtual world, we're not just going to have adults, we're going to have children too. How do we generate avatars for children that are childlike? Now, if we think about generating child avatars or generating child characters, there's a long history of creating very compelling child characters. And I believe modeling the geometry is not going to be so different. Now, of course, we're not talking about very, very young kids where you have to model soft tissue and so on, babies. We're talking about kids. Modeling the geometry, we have a good idea. Creating various kinds of appearance, rendering in this style versus that style, all of the work that we know from adults can be leveraged for this. Motion, on the other hand, is an entirely different game. We want an avatar that moves like this and not like this. This would break it. So let's think about the classes of approaches to generate motion for child characters. We can use keyframing. Keyframing involves creating the motion by hand, right? Each frame created by hand. Very laborious, very time-consuming, not a suitable approach for interactive applications such as VR. Physical simulation. There's a long history of work in physical simulation, and excellent work has been done in terms of creating responsive characters for games. The trick here is that there are hundreds of parameters, and we need to get them just right. Otherwise, your character will crumple and fall after taking few steps or encountering some unknown terrain. And then there's motion capture. So about 2 decades ago, motion capture became a really usable technology, and it really transformed how motion generation was thought about. We then had an ability to leverage large databases of recorded motion. And there were techniques that were developed as to how this motion can be used, how can it be reused, how can it be used for different environments or different characters, different sized characters. How can motion capture databases then feed into tuning parameters for physical simulation and into making keyframing better? So motion capture databases and their availability really transformed the way we thought about generating motion for avatars. Wouldn't it be nice if we could do the same for child characters? If we had access to child motion databases, we could simply leverage this 2 decades of work and use those same approaches to generate to generate child characters. The challenge here is that children are not like adult actors. They don't listen to instructions very well. They lose patience. They don't have very good task compliance. You ask them to do something, they'll do something else altogether. Right? And these are not technical problems. So this is not a problem related to how high the frame rate is of our cameras or whether we can interpolate across dropped markers and so on. These are challenges relating to the fact that children are children. That's not something anyone can change. So we said, okay, what can we do about this? Can we just use adult motion capture data? What if no one can tell the difference, right? We'll just fake it. We'll just use adult motion capture databases. And I'll talk to you about research that we did where the answer was not really. So if you were to take adult motion and child motion, and you were to remove appearance information, and you were to scale the child motion, viewers can still tell which motion came from which actor. So the two are not exactly equivalent. Then we ask the question, can we transform adult motion capture data to appear childlike? There's a lot of work on motion stylization, motion transformation. Can we use this literature to just kind of, tweak the adult motion capture data and then it will become good enough? And the answer to that is perhaps we can. So what I'll do is I'll give you an overview of both of these research questions, just in just a little bit of an overview, and we can always talk through the details. So how do we answer this question? Can we just use adult motion capture data instead of child data? Well, we look at the literature in child development. What does that tell us about child motion? We know that children typically move faster than adults. This literature also tells us that very young children exhibit unstable postures and oscillations in their motion. Very, very young children. This literature, however, was developed with the goal of quantifying and detecting sensory motor impairments. And so they're not directly comparing children to adults, right, for the purpose of matched actions and so on. We also know that there's literature in the computer vision and graphics community. It is possible to classify, or it has been shown, there's evidence that it's possible to classify child versus adult based on stride length and stride frequency. So there are distinguishing features in the motion itself, regardless of appearance. If we look at what are the mocap databases out there, they're overwhelmingly mocap databases of adults. There's very little child mocap data available. And the goal of all of this literature is automated and semi-automated analysis and generation of motion. So it's been collected with that in mind. So given that there's vastly more adult mocap data than child data, our first task was to create a data set. So this is a data set of matched actions. 50 actions, 10 children, 10 adults, all responding to the same prompt. Given this database, we then took 6 actions that are very kind of dynamic actions, right? Easily interpretable by both children and adults, and that have been studied before in the fields of kinesiology and human performance. And we rendered them as point light displays. So point light displays are what you see over here. There's no appearance information. They're literally point lights or markers at key locations on the skeleton. Point light displays have a long history of being used in kinesiology and human performance, starting with Johansson's studies in the 1970s, where he showed that people, if you were to show them this point light display, the moment it starts moving, so the moment this picture turns into a video, people are able to identify the action, they're able to identify the identity. There's work to show that people can identify if the actor is male or female. They can identify if it is themselves or a friend or a stranger, right? So this is really a very well studied paradigm to understand human motion. Right? We were the first to ask, viewer, can you tell me if this is a child or an adult? That is something that was not known as part of this literature. So we did a study where we asked viewers, can you identify if this is a child or an adult? And we did not give them appearance or absolute scale, right? So they couldn't say, oh, this is smaller, must be a child. 24 participants were part of our study. And here is what they saw. They saw a point light display. Here is the picture. Actually, it moved. And they were asked, does this motion belong to a child or an adult? So this is a two alternative forced choice or a yes-no type experiment. Right? There are some technical differences between the two. Ours was a yes-no type experiment. And we asked them, what is the action being performed? Because this was an online survey. So we needed kind of a sanity check just to make sure that they actually watched the video. And here's what the results look like. At a very, very high level, if we were to look at child actor and adult actor, and the percentage of times participants identified correctly that the motion from a child actor came from a child actor, both of these were above chance. So that tells us, well, these two motions are not equivalent. People can identify just from these point lights whether it was a child actor or an adult actor. So we can't really just fake it. We can't just use this motion capture databases to generate child avatars. So that brought us to, well, we haven't quite given up yet. Think of all the databases that are available and the ease of capturing adults. What if we could just childify the adult motion, right? What if we could do this? So there's something that goes in our favor in terms of childification. The first is children move faster than adults. This is something that literature has found. If we were to look at all of the work that has been done from the algorithm side on motion stylization, there's a lot of work that has been done on changing the character's gait, right? To convey different kinds of emotion or different kinds of personalities, right? You turn a happy walk into a sad walk, or you turn a regular actor into Donald Duck, something like that. But all of this work leverages large motion capture databases. And so it's not something, that is our bottleneck. It's not something that is directly applicable to the problem that we have. If we were to really look back, though, we find something interesting in the robotics and biomechanics literature. These folks wanted to transform motion from one character to its scaled version. There's some excellent work that has been done on this because they were developing controllers, physically based controllers for robots and simulated characters. And the idea was, if you tuned your controller for one particular character, could you then create motion for a robot with slightly different parameters, right? A scaled version of it or a scaled character. Right? An example of work that they showed was controllers that were created for an adult being used to create motion for a character that was child-sized. Right? This is fantastic. This tells us that these scaling rules that were used are probably applicable to adult motion capture data too. The key open question, does the resulting motion appear childlike? That is not known. If viewers were to look at this character, would they think it was a child moving? Would the motion be childlike? So our key idea was, okay, we're going to apply the dynamic scaling laws to create childlike motion using adult mocap data as input. And then we're going to evaluate the effectiveness of this method. And the important thing is, we want a metric. We want to be able to quantify how well this method does. So I'll talk about the steps of the dynamic scaling laws at a very high level. The algorithm itself is very, very nice. It's very easy to implement. We start with adult motion. Here's what it looks like. We scale this adult motion so that the height of the character, the limb length, and the displacement are simply linearly scaled to the size of a child. Right? And there are some nuances over here. How do we do it so that the limb connectivity is maintained and this character is not floating in midair? They're still maintaining ground contact and so on. The result looks like this. Okay? It's just kind of like a miniature child. And then this motion is sped up by square root L. And that's what it looks like. That is the dynamically scaled result. And what this does is, basically the set of rules, it maintains gravity in the case of a ballistic jump. So the resulting motion is in that sense physically correct. Now that we have dynamically scaled motions, we conducted another point light display experiment where we had 3 actor types: adult, child, and the result of the dynamically scaled procedure. We have 4 actors per actor type, 6 actions. That gives us 72 videos in total. Right? We had 4 individual actors. The order of the videos was randomized, and 24 participants were asked to rate whether this motion belongs to a child or an adult. And our goal, of course, is to see, well, the dynamically scaled results, what were they classified as? Did people think they come from a child or an adult? Okay. So in our data analysis, we asked 2 questions. First, are our participants able to identify child and adult videos correctly? At least they should be able to do that, because we know from our previous experiments that it is possible to do this. And if they're doing this correctly, means that they are kind of sincerely doing the task. And yes, all of our participants, except 1, were able to correctly identify the child and the adult videos. The next thing we did was ask the question, do participants attribute the dynamically scaled results to a child actor? Okay, so here's what this looks like. We checked to see how many times a child was classified as a child. That's about 67% of the times. How many times is an adult classified as a child? That's about 30% of the times, right? And this gives us bounds, or in other words, it gives us a scale. We know that people get things wrong. Even an adult is classified as a child 30% of the times. Even a child is classified as an adult 30% of the times. So even if we were to reuse original child motion capture data, we're only going to get people to think that it's a child 70% of the time, 67 to 70% of the times, right? So the question then is, where is dynamic scaling in this? Here's where it is. So dynamic scaling takes us a little bit along the way from adult to child, right? And because we have a metric, we can quantify how far along it takes us, right? What this gives us now is a framework. Now that we can quantify how far along the way we came, we can ask the question, how do we cover the rest of the way? Right? And this is where we're now starting to look at all of the other literature. Can we use nonlinear scaling? Can we use skeleton retargeting? Can we do a combination of these? And then, using the same kind of a test paradigm, measure how far along we come. At what point do we see diminishing returns? What is the combination that gives us the biggest bang for our buck? So, to summarize, I've talked to you briefly about 3 ways in which we have used perception for a variety of applications for social platforms. In the very near term, we can quantify attention for improving UX design. Looking a little bit further out, we can use information from the eyes to be able to do performance analysis. We can use information about perception to be able to generate virtual avatars. And we'd like to be able to do all of this because really, I do believe eyes are the windows to our souls, and there's a lot that we can do if we can infer information from a person's eyes. Thank you.